So, hello, I am back after a long time, and this time I am trying as much as possible to learn QFT, quantum field theory, and it is definitely too hard. I mean, I don't know, like, I'm studying quantum field theory almost every day, still, like, got nothing, but all I found out so far, I mean, all I care right now is that this is an extremely successful theory which gives experimental results matching up to 8 orders as far as I have heard. And if that is the case, I will not give up. I will understand as much as possible, and I will go to any extent, uh, any rightful extent in my hand, even if it requires me to learn from AI, learn from any textbook, any resource, journal, whatever it is, because at the end, all I care is the right information. And yeah, so where to start? Like all these heavy terms, like what should I say? Quantum fields, of course, and I really want to become a particle physicist, no matter what. And then we have uh, not just a particle physicist, one of the best particle physicists. I don't know how will I do it. I don't even know what it means. I will keep trying as much as I can every day. So then we have these words called renormalization. Then we have Feynman diagrams, of course. We have propagators, and then we have what do we have next? Regularization. Like I can open a quantum field theory book prescribed for me, which is very standard book. Almost anyone who is studying quantum field theory dedicatedly will know about this book, very likely. And so, what all do they have in this book? Like they have a lot of stuff in this book. Like quantum field theory is an ocean. Like I mean, I can't believe like there is so much. You have to have a good grasp of special relativity. Uh, so much of linear algebra must be known. Uh, you must have a good grasp of quantum mechanics. Uh, so much. Like I don't know where to start from. Like okay, and I think they have this option of oh wow. If I click a section, I just go there. Wow, this is very nice. This okay, so they have so much. Like I have to like I don't know if I can. All I want is at least I want to understand first four chapters and try solve as much as possible, solve problems and things. I want to become good enough, good enough to start my PhD in particle physics. Yeah, finding a guide will also be a task in itself, but let's see what happens. And so much of stuff. I mean, so many topics to cover here. Like, um, and right now, what I will, and yeah, I will never hesitate to use ChatGPT. Of course, I will try to find the sources and verify the information, but I have to in this fast moving world. I have to, and yeah, so many things. And also, we have to spinners are there. Spinners, Feynman diagrams, propagators, renormalization, regularization. Oh my God! Like it's all going to be hell, I guess. Uh, Today I will try to derive the quantum field if I can, the Klein-Gordon field. Then tomorrow I will see what I can do later. Klein-Gordon field. So the Klein-Gordon field, and one of the ways, there are many ways, but let me see which way I know, which way I can use whatever I have learned. It's very difficult for me, but yeah. So the most important thing is harmonic oscillator here, right? So if I have a, in quantum mechanics, what do we do? I have a system, a particle having both momentum and position at any instant of time. Uh, so yeah, I forgot this half m omega square, and then what we do is try to find its energy values, possible energies, and to do that we have ways of our own. Uh, we take this assumption that the lowest possible energy, uh, we have this operator uh, uh, which I should say like reduces the state. So if I have this lowest possible energy state, I will just get 0. This is the first assumption, and now what we do is we define two operators, right? We define the step up operator and step down operator. And this has mathematics of its own. I don't think I should go through this to understand the physics. This is one of my biggest bad habit. I won't repeat this. I have to grasp the physics. Of course, mathematical rigorousness necessity will always be there, but if I keep chasing it, I will never be able to get the bigger picture, which is, I think, more important right now. So let's just go to some source and just get it. So here we go. So we have this. Uh, so let's see the ladder operators. So yeah, here we go. These are my ladder operators. Let me write them down. Mhm. Some fancy operators. I can replace this with x by the way. No? Just let's use x here instead. X square, and here comes the picture. So now here we go. Here we have it. And then what we have to do is now what we have to do is we have, when we take the commutator, right, of this a and a dagger, what happens? Let's see. I want to speed things up. So square root just gives me m omega by 2h cut. I have to keep a track of the bigger picture. If I fail to do that, I don't think I have done anything, honestly. And yeah, we do remember that x cap b gives I h cut. So let me do that. So the commutator of x with p multiplied by minus I by m omega, and then commutator of p with x with uh, minus I m omega. No, I mean I m omega. So m omega gets cut, and now I get minus I, let me take out, and by 2 h cut. So this thing is I h cut, and plus minus I h cut, because there is this p x cap, right? And since I took minus I out, there will be a minus 1 here. So as you can see, minus I times I is 1, 2 h cut by h 2 h cut, which I wanted, I think. So basically a cap a cap a dagger gives me unity identity. so this is the case, and if I do mathematics, I can write the Hamiltonian in terms of this ladder operators, which has been done many times in any bachelor's quantum mechanics course. And let me see, here we go. So here we have it. So this is how they write it apparently. So the Hamiltonian in terms of the ladder operators can be written as, and yeah, we know the ladder operators. And here right now there are two kinds of pictures, right? This a and a dagger can be thought of as operators which raise or what should I say, raise. Then what is the opposite of raise? Lower, uh, raise or reduce, I will say raise or reduce the energy state. But there is also another picture where instead of raising energy states, raising or reducing, particles get created or annihilated. But created and annihilated right now we won't use, we just think it as raising and reducing energy states. So this will be h cut omega uh, a a a dagger a plus 1, I mean half. This is how we can write the Hamiltonian. And so he, okay, this is fine so far. Now what we are going to do, I want to have a field, right? A quantized field, which is a hard thing to do. I haven't much ever done stuff in that. Uh, but so if this is the Hamiltonian for a harmonic oscillator, what more can I do? So mm, there are a lot of crazy ideas, like uh, let me just have some source and see what they have done, then come back. I recently saw a lecture by this professor called Sunil Mukhi. They are very nice, the lectures. So let's go to Sunil Mukhi. If they have a book, it's even better. Sunil Mukhi, quantum field theory. I think they do have a like a kind of notes, right? This is what was taught by, yeah, even in the lectures it was same. And honestly speaking, relativity is required to understand quantum field theory. Without relativity also it is very almost impossible. So let me just go through this again. I guess there is so much going on behind the scenes, like if we don't keep the track, it's like complete loss. Let me send this file somewhere, and I will not hesitate to use ChatGPT, by the way. If I need it, I will use it. So let me just go from the start, whatever is being discussed here. So he's saying that validity of quantum mechanics is experimentally demonstrated by photoelectric effect, atomic spectra, and all those things. Yes, atomic spectra was one of the best. I think for me, atomic spectra is like what should I say? Something that convinces me most about quantum mechanics. It's like, okay, this is working regardless of whatever assumptions we took. uh, and also special relativity is experimentally proved, because speed of light was measured to be constant. Doesn't matter however we measure it. And also time dilation, like we shot a muon close to the speed of light, and apparently it did age slower than it was supposed to be. And then, yeah, so quantum field theory, one of the objectives of quantum field theory was to unify special relativity and quantum mechanics. And Uh, so yeah, how do we extend relativity to incorporate quantum mechanics, or vice versa? You can say, how can we extend quantum mechanics to incorporate relativity? So this anyone who has studied quantum mechanics uh, properly will obviously know it. Uh, or anyone who even got introduced, sometimes they just see this. Uh, this is a non-relativistic, and this is a Schrodinger equation which is non-relativistic. It's like it's really boggles me, like the way Schrodinger equation was built. You just write this Hamiltonian down, general Hamiltonian. Then you say, okay, there is this abstract quantity called wave function which has all the information. You just multiply it. So basically this is a vector, and this Hamiltonian is a operator. So it will have all these different eigenstates of energies. We don't know what it is, but we keep it as it is. And we just write it like this. This is the Schrodinger equation at its simplest. But here what we do is this p square, this p, we for some reason if we assume that wave function is plane waves, is nothing but comprises of plane waves. uh, what is it, ikx, something like that. So momentum is something like this, and we just plug this in and we get the Schrodinger equation. Honestly, every concept I am talking about is something which I can sit for hours and hours just thinking about them, but I don't have all my life, and I really want to do something good in this, and there is no time left to regret. I have already lost enough stuff, honestly. Really. So now let's go next. So this is the Schrodinger equation. Provided our particle is not going uh, close to speed of light, particle is not traveling at a speed close to the speed of light, and then so relativistically this is the equation. The energy of the particle is given like this. So this equation has also been, as far as I know, experimentally verified. So we will do the same thing here. We will just shove everything in. So energy is given like this in quantum mechanics, right? Uh, There were dirty, but there is a subtlety. Like the problem is when you think of energy in classical non-relativistic case, it is just p square over 2m. It is just p square over 2m, and uh, but where here energy in relativity is so this is non-relativistic and this is relativistic. Here the energy is given by some kind of a hyperbolic relationship. So you have this plus or minus square root of uh, p square c square plus m square c4. Uh, hmm, so here we go, and so this is it, and here these are the things like and what should I say? Uh, so energy in the for a free particle case, when it's free kinetic energy, it's related by the moment. It's just depends on the momentum. But here the problem is it also depends on the rest mass energy plus there is a square root. So I don't even know how will the operator correspond. It might look very ugly, right? Uh, if I just blindly write, what if I do something like this, which I don't think anyone will do. But suppose, right? I wonder why I never saw this, but so something like this I might do, right? Or I might just keep things like this as they are. Who cares? E square is p square c square plus m square c4, and and if I just do this, what should I do? Del square by del t square. This side will have del square by del t square with a h cut, and this will have a h cut again. I think it will have a h cut square. Yeah, h cut square. Uh, Del square by del x square. Okay, I'm going nuts here. C square will be there. I can just take the c square here. I will just do this plus m square c square 4. I can do all sorts of things, but let's just stay, what should I say, loyal to the uh, formalism made by uh, numerous people taking decades. So this is some stuff, and he took C1 natural units, and here in the notes it's showing how it can be approximated as p square by 2m, and all that is nice. I mean, sure, why not? So and here you can see, okay, same thing here as I did, okay, as I wrote here, exact same stuff. C is 1, okay, it's written here. You see, you just substitute it blindly, which can be done, I mean, and doing more math. So if you write this further, you can write something like this. Del square by del t square minus, and also I have to check out what metric they are using, I mean what notations they are using. So here we go. uh, okay, the notation they are using is uh, hmm. So I suppose they are using huh no need of this minus and plus. Okay, fine. So they are using this notations. So neta, there is this metric which is being used, which will be like this. Okay, so here it will be something like this. and basically so this can be extended to xyz, right? So we have this special symbol which is given like this: del square by del t square minus del square by del x square minus del square by del y square minus del square by del z square. So if this is the case, then some Klein Gordon equation can be written something like this. And also I wanted to tell I am using h cut and c as 1 because apparently this doesn't affect the physics, but when you have to calculate precisely the observe observations, you have to plug everything back so that you can predict the results whatever you are doing, maybe particle physics, detectors and stuff. So right now we want, so here they have mentioned used it used h cut not equal to 1, but they have taken c as 1. So this is Klein Gordon equation and free Klein Gordon equation. So what do they mean by that? Oh, they mean there is no potential involved. Yeah. So yeah, so let's see further. So we can have a general solution of this equation which they have given, which is thankfully a plane wave solution again, but a plane wave in 4-dimension space, space time. So let me write down again. Also let's bring back h cut. So I have something like this, right? And we will try to be as uh, what should I say, I will be heuristic here, because right now I care more about the physical picture than whatever is there, than the numerical subtleties or calculative subtleties. I don't much care about them. uh, and so here we have these things. uh, so fine. So what, so now the thing is, again the relativistic relationship E square is m square plus p square, where c is taken to be 1, and this by the way is not the 4 vector here. I think this one is the 3 vector, 3 vectors. So if looked carefully here, this is nothing but E square minus uh, px square minus py square minus pz square. This is what this overall thing will give, which will again give me m square, and this is only possible if I have something like e power I, uh, let's say uh, et h cut. Let's also bring h cut minus px x, px times x minus py times y minus pz times z. Then as you can see, if you differentiate this thing twice, e will come out. I think I will also need a minus here. So according to the metric we are using, which we are using here, this neta metric, uh, according to this metric, what we will have is something like this: minus I h cut, uh, uh, what should I write, p mu I guess, oh wait, I think I, yeah, x mu, this is what we will have according to the metric, and that's what it is written. They have used k in here instead of p, but they both mean the same thing in a sense. So you can and they are using like there is this relation p is equal to h cut k. You can go one way or the other. That's not an issue, and you will get the physics will be the same. I don't want to get into that. And according to this, negative energy solutions are allowed, right? Like that's what the solution says. And so if I plug this in my free particle Klein-Gordon equation, uh, I am supposed to be getting uh, results satisfying the differential equation. And so the negative energy solutions, so what should I say? So he has differentiated this with respect to time once, then which you get k naught outside, uh, and k naught will be here, which is given. It is just again because this is from the relationship from special relativity, nothing more than that, energy relationship. And so normally we can just restrict ourselves to positive energy solution, uh, and why not we just do the same in relativistic case and say maybe negative energies makes no sense. Why not? uh, hmm. But the problem is there is this belief in quantum mechanics that once you have these energy levels coming from the Schrodinger equation, there will always be transition from one state to other. Particle can do that. So if I have both positive and negative solutions, this means these energy states have no upper end or lower end. For example, when I have a harmonic oscillator potential in classical case, non-relativist case, uh, let me write that down. If I have a harmonic oscillator potential, uh, then I have this assumption, right? Like it was, I don't remember what was the justification for it, but if I there was the lowest state, there is no state lower than that. But in this case of special relativity for a free particle, there is no such thing as a lowest state or a highest state. It is all chaos now. Like which state will the particle be in? There are literally so many states which the particle can be, and doesn't matter how much energy I suck up. It is basically telling there will always be more energy left. I can keep going down and down, which doesn't make sense. At least this is what I'm trying to say myself to go forward in QFT. So next what we do is we have these Maxwell equations, and of course we have this what do we call this thing, the tensor, the electromagnetic tensor, and these relationships. Maxwell equations can be just described using this tensor, and mm, so electromagnetic field, right? An electromagnetic field is a 4 vector at each point in space and time. So he is using this uh, quantity as an electromagnetic field. A0 is the what should I say, scalar potential, and A1, A2, A3 is the vector potential. So we can try, what should I say, quantizing it. uh, so we have these, so this, okay, this equation is apparently important. The obvious relativistic field equation one can write down for this, analogous to the Maxwell equation for, so in a sense, this is a field of a particle which is massless, and uh, I can't say much because I don't know any good either. uh, so phi is a scalar field, at least that's for sure. uh, so we have this, uh, and this. So I wish I can do better, but there is so much going on really, and hmm, so much more, and periodic boundary conditions, here they come. I honestly really like these notes. Like, I would like to study them more and then comment on them, I guess. I mean, I will come back later in next video. I would like to understand, but they neatly, how should I say, finally got this field which I want at the end. If I got this, I will be very happy. And then they develop this new hypothesis or things like that, new, what should I say, proposals, that okay, let's have these and see what happens later. And they kept going, normalizing things, time evolution of the field, like how would it evolve with time. And then finally these are our fields, creating and annihilating particles and antiparticles. But uh, antiparticles come up only if you have complex fields, by the way. Real fields don't have antiparticles, and you just get what should I say, spinless particles. And causality. So there are some comments on causality here, which is very nice. And so this is a 2-point amplitude calculating function, and we have more, we have more, we have more, and more and more appendix. Too much to learn, honestly. Lorentz transformations, the Feynman propagator, action and field equations, and more, keep going. Interactions. I think I can't go any further because there is too much to learn, like seriously. Okay, time ordering, here it comes. Uh, Too much to understand, too much time will be taken. It can't be, uh, really, like, look at this. This is something else. And Wick's theorem. Okay, Wick's theorem. That's something, and we have this. All this should be learned. I will do it. Lorentz gauge, electrodynamics. Hmm. This will take a lot of time. I really want to get good enough, but this will take a lot of time, honestly. Thankfully, I have practiced enough Clifford algebra, even though I had no physical intuition. So I think this will help me. I practiced a lot of Clifford algebra. I hope it helps. So water spinners and all these things. This will take me a lot of time, but I will come up on top. I will win no matter what. Thank you for watching, and bye. Whoever watches, I don't know why you watch it, but